Just looking forward at my schedule here. The next one I want to do is the predator-prey model. So let's make a new model. I'll call this predator-prey. Click OK. Now I'll just start this out at concentration as well. Again, I will change that later just to show you sort of the differences. So predator-prey, now instead of a single variable, I'd like two variables. I'm going to have the myRabbit variable. So we start out with some initial number of rabbits, and I get the best results when I start them off at 1,000. So we have rabbits there. Add a second variable. I'm going to call this fox. Foxes also start out at 1,000. So these are both concentration modes. Then I'm going to add some parameters. So the first parameter is going to be the birth rate of the rabbits. Our birth, and I'm going to make this 10. Second parameter, let's see, this is going to be birth rate of foxes. And note, if you put invalid characters in there, we catch that for you. We do the best I can. We've done the best we can to make this as user-friendly as possible. So f birth, and what do I have for that? 0.01. And then I'm going to add a third parameter here, which is going to be f death underscore death. I'm going to make that 10. Great. Okay. So just to be clear, you don't have to click save variables or save parameters, but I like to because this gives us this real nice interface here, or real nice description of everything. Okay, so we have our foxes, we got our rabbits. Now let's talk about our interactions or reactions. So let's see. The first one we're going to do is we have all of these different ones, but really what I want is that one rabbit goes to two rabbits. So really A goes to 2A, but I don't really see that in the list here. Now that's common. These types of reactions come up a lot, but there are so many different kinds of reactions that we can't possibly come up with all of them for you. So instead we have custom mass action and custom propensity. So this is a mass action reaction. So we're going to click custom mass action, and I'm going to call this our birth. So you can see the summary already says rabbit to rabbit, just because we're guessing here. But down over here, you can see the reactants and products boxes. So you can see that reactant is one rabbit, and then I could add another species if I wanted, and I'll do that in a second. But I want this to be one rabbit goes to two rabbits. So I'm going to add this here, and you can see one rabbit, arrow, two rabbit. So that's going to be my R birth. So rabbits, just every rabbit makes more rabbits. Then my second reaction is going to be that when a rabbit and a fox interact, that gets me another fox. So R plus F equals 2F. So add reaction, R plus F equals 2F. That's not there either. So I'll do another custom mass action. So this is going to be fox birth. So fox birth is going to be that we have one rabbit, so that exists there, and then I'm going to pick the second species, fox, add. So now I have rabbit plus fox. And then over here, I want to say, well, that's going to produce two foxes. So rabbit plus fox goes to two fox. So this is how the foxes interact with the rabbits now. So we've got this. I need to check back here. So, okay, the rate parameter was R birth. But for this one, the rate parameter is going to be F birth. Then we're going to add a third reaction. That third reaction is just going to be, nobody eats the foxes, they just die of old age. So this is going to be a destruction reaction. So this is going to be fox death. The destruction reaction is that fox goes to nothing at F death rate. So I'll click save and just confirm. We've got rabbit goes to two rabbits at R birth. We've got rabbit plus fox goes to two foxes at F birth. And we've got a fox goes to the empty set at F death. So this is our basic stochastic local Volterra predator-prey model here. And let's see. So we can just take this now and do our little run. Ooh, I think I did something wrong. Rabbit goes to 2 rabbit. Yes. No, seems to be right. Let's just run it again one more time just to be sure. All right. I'll tell you, I got slightly different values when I ran this earlier, but that's fine. Let's scroll up here and do the same thing we did before. We're going to edit our variables, change this to population. Population, and click Save Variables. Now we'll click Simulate. And then, yeah. Okay. Simulate Preview. Okay. Now we've got the classic local Viterra phase offset oscillations, right? So what happens here is we initially start out with 1,000 foxes and 1,000 rabbits. Well, the foxes start to die off of old age, but the rabbits start to produce. So rabbits go up. As a result, the number of rabbits available to the foxes goes up, so the foxes go up. But then the foxes start eating the rabbits go down, and then as a phase offset, the rabbits go down, so you get this double oscillation here. Let's go ahead and change our numbers around here and just see if we can't get something that looks a little bit prettier. Right, simulation time 10, and now I'm going to sample it 5 times more frequently. Right, now you can see we start out pretty jagged, and note we're still stochastic here, right? All integer values, but then very quickly we're getting this very nice curves run out here. So that is the local Viterra deterministic and stochastic simulations with their oscillations here. So, turn to project. Okay, so we've got our predator-prey model. I'm going to go ahead and show you a different way. So I'm going to use new workflow using this model. And now you see, here's our full set of workflows. So again, I want to do an ensemble simulation workflow. Gets us here. Let's see, I will choose SSA and 100 trajectories, perfect. And then I'll click Start Workflow. Perfect. Okay, so you can see that all of these simulations are all hovering around 1,000, the initial condition, but the oscillations go up. So it looks pretty interesting. If we plot all the trajectories right on top of each other, looks pretty messy, but here are all the rabbits and foxes buried within there. We can look at our mean and standard deviation. You can see the standard deviation is sort of going up. And then the mean, well, those mean values are oscillating along with it. No logs, great. And here is our everything. Excellent. Okay, so that's an ensemble simulation. So usually at this point, when I'm making a model, I want to do some sort of post-processing, something else that shows what's going on inside of my model, do some analysis on it, make specific plots that I need for my paper that I'm writing. So to do that, I have to write some custom plotting, custom code. So we facilitate that by, so we're going to make a selection predator-prey by the Jupyter Notebook workflows. So I'm just going to do an ensemble simulation workflow. And what has happened is the model that we've built using StochSS, the interface, has been converted into the Python code that makes up a Gillespie 2 simulation. So all the simulations we've been doing under the hood, the actual simulation engine has been Gillespie 2 for both ODE and the stochastic simulations. And I'm going to show you now exactly how to use Gillespie 2 and one of the big powers of StochSS is that you can just take your model, create it very simply, export it to this code, and then do whatever you need to do with the code. So a GlassPy2 simulation, you import GlassPy2, and then, as a convenience, just to make things a little bit more terse, we import all the model, species, parameters, reactions. And just to be clear, biochemical species or species and variables are the same thing. So I might use the word variable, I might use the word species, but yeah, they mean the same thing. So to create the predator-prey model, we make a new Python class. We name it the name of our model, and it extends the GlassPy2.model. Its constructor here simply sets some initial conditions here, but then we add a parameter with a parameter class rbirth. Same thing with fbirth, fdeath. We add our species, rabbit and fox, with their initial values and their mode. So these are discrete mode instead of continuous mode. And then we add our reactions with instantiating a new reaction, rbirth, rdeath. And you can see that these are exactly what we put into there. We take our predator-prey model there. And then this configure simulation really is not too important, but it does help us build. I'm going to change this to one trajectory at the moment. But then I'm going to do, so I click on this, and I'm just going to shift return and execute this notebook for you during the simulation. So just to be clear, so we create a class called predator-prey, and then we create a variable, which I'm going to call model, but you can call whatever you want, and instantiate that predator-prey class. Then I call model.run, and I'm passing in these keyword args, but really the only argument is this number of trajectories equals 1. So model.run produces a result object. That result object then has a lot of features on it, and one of the features is a plotting feature. So I can just do results.plotly, and here I have right inside my notebook another, looks pretty much exactly like we were doing before, right? 0 to 10, right? Because I set the time span from 0 to 10, sampling every 0.01 seconds, just exactly like we did on the interface. And then there are additional plotting functions. So this is the matplotlib version of the exact same plot. So we have plotly and matplotlib. They're both very useful. And then you can save this notebook, you can download it, you can export it. It's very useful to do any of your post-processing within these Jupyter notebooks. Okay, so now I'm going to go ahead. So I click save on this. I can just close this. So now I go back to this page. And I'm going to click back to here just to show you. So this doesn't show up in our workflows now, right? Only the StochSS workflows show up here. However, click down here in advanced. You see we can browse our files, and then you can see all of the files in our project here. And here's that predatorprey.ipynb. That's the notebook. I'm just going to double click it, and then we're back. So StochSS's file interface is set up the exact same way, or deeply integrated in with the Jupyter infrastructure to allow you to just go back and forth and open those files directly. Great. How are we doing on time?